Hello, my name is Dr. Tom Kamalo, and today we're going to show you how to take tyrosine, seen here, one of 20 commonly occurring amino acids in the human body, and sketch it into a three-dimensional model of dopamine, which in the human body, dopamine is naturally derived from tyrosine, so it makes a pretty convenient model to sketch from tyrosine here. For this, we're going to use the program VEGA ZZ, which is freely available from an Italian group, I believe, at this website. I've not met them, but they're pretty good guys. They're putting out free software for us to use. And you can download here, and I will leave this up long enough for you to kind of see the URL. Also, just Googling VEGA ZZ will bring up the program in your Google results. So now let's go to the VEGA ZZ window. We're going to close these tabs. Here we are in VEGA ZZ, which I just started up. Sometimes it detects the processors slightly different. It says I have 8 atom processors. I actually have an i7 in this computer. And so what we're going to do first is we're going to go over here to our little menu here, and you can see that should say add fragments. When I scroll over that, we're going to go add fragments, and we're going to go down to amino acids L, the type that most commonly occur in the body. And we're going to scroll down to TYR, which is the abbreviation for tyrosine. So here we have our tyrosine. Three-dimensional model of tyrosine. You can see you can rotate it in VEGA ZZ by pressing down your left mouse button and holding it down. And basically, we are going to accept the defaults here, and then we're going to close this window. So, if you remember from the picture, dopamine was missing this carboxylic acid group here, and also had an added hydroxyl group right about here. So what we're going to do is go to Sketch. We're going to add that hydroxyl group, which would be sp2. So add that, and to add a atom in VEGA ZZ, you set up this window here like that, and then what you do is just click on the atom you want to connect it to, and there you go. We want to remove this hydrogen right here, which we just removed. And again, as I was saying, this carboxyl group is also not in dopamine, so we removed all that. So now we have something that looks somewhat like a dopamine, but not really. Still missing some details. So first we're going to do the hydrogens, so add hydrogens, and we're just going to accept the defaults. And it gives us a somewhat dopamine-ish looking molecule with the protonated amine at the end, which is what we're going to use. We're working with physiological pH, alternate physiological pH. The amine at the end of dopamine would be protonated. Our hydroxyl group has a hydrogen. Basically, I should have gone over before. The whites are the hydrogens, the reds are oxygens, these greens are all carbons, and this blue is a nitrogen. And what we're going to do now is the most important part of molecular modeling at this level. Is you want to calculate the charges and potentials, and we'll assume we're doing this for a docking experiment using autodots. We'll use autodot, gas your charges, and we will fix those charges. So you have a charge of 1, which is this extra proton over here. And now, to get the structure correct, we're going to use amp, we're going to use a minimization. Whenever you change something in your molecular modeling, you have to do a minimization. Or you're just energetically not going to be really that kosher. So I have a lot of minimization steps. I have 30,000 minimization steps. It won't run for this long. And I'm going to use just a simple default trust algorithm to minimize this molecule. And when I run this, the molecule is going to bend and twist, and it will turn into the lowest energy state. You can think of this as if you made a model of a room, and you had a book on a table, and then you wanted to remove the table. Well, that book would be floating in the air, theoretically, if this were like a molecular model kind of scenario. And what you want to do is you want to return that room to the lowest energy level. So you can think of like we're putting the book on the floor underneath where the table used to be in order to make this more energetically realistic structure. We run this, you see it's wiggled around a little bit, and we have dopamine. And there you go. And we would close this. We would go up here to File, and we can save as. And we want to save this as dopamine. There are different formats you can save it as. You can save it as the PDB-QT for Autodoc, but that's not. It might work. I'm not gonna say it hasn't. I haven't tried that. Usually, what I do is when I'm doing the PDB-QT, no, actually that won't work. No, I don't believe that would work. So I would say it's the mol2, and I would convert it in the to the PDB-QT using Autodoc tools or using a script that calls the auto setup on Autodoc tools. And so there you go. That's your dopamine molecule. Dopamine is a signaling molecule. Too much of it in some parts of the brains, you end up with something like schizophrenia. Too little of it in certain parts of the brain, you end up with something like Parkinson's. Like most things, the balance is really the key. I hope you enjoyed this video, and I hope you'll check back the channel another time. Thank you.